Okay, everyone. So this is this extra um, bit of the lecture. It's not mandatory, but it's suggested. Let's just review everything we discussed in the second part of the video. Let's start with the square well. This is all familiar. Here's a square well. Here is the ground state. Here's the first excited state. It's probability density I'm plotting. Here is the second excited state, third excited state. Number of nodes increases, number of empty nodes increases. Notice that when we go to top of the uppermost excited state, you see that it spills over into the non-classical regime the most, right? In other words, the penetration depth increases with M. We've discussed that, right? Because the penetration depth is proportional to kappa, which is something like proportional to the square root of well depth minus E, which is, well depth minus E is very small here. So kappa is very small. In other words, the decay rate is very small, so it penetrates very far. We've discussed that. We've discussed that if we make the well narrower, the energy levels split. We make it wider, energy levels come closer together. You have more levels inside. We've discussed that, of course, if we make the well deeper, you can fit in more energy levels. We've discussed all that. All of that is here. Now, this is probability density that I'm plotting. What about the wave function itself? Well, first of all, the wave function is complex because you multiply by the time part, which is e to the minus I omega t. So it has a real part that goes like cosine omega t, and has an imaginary part that goes like sine omega t. So not only you have the spatial shape of the wave function, but it also breathes. There's a cosine omega t and sine omega t. As long as I look at any one mode, the magnitude is time independent, and the square of that, aka probability density, is time independent. But I can superpose two modes. So let me superpose mode number 1 and mode number, mode number 3. Okay, so I'm gonna do this kind of a superposition. I'm gonna normalize that adjusts these coefficients to normalize the probability density. And now we see, oops, now, just a second, there was a malfunction. So let me do this superposition. So 1 and 3, I'm gonna mix in 1 and 3. I'm gonna normalize, I'm gonna apply. And now we see that the probability density breathes. It's not a time independent thing. You see, I'm mixing mode 1 and mode 3. Where does that time dependence come from? That's what your non-textbook problem, what your non-textbook problem was about. And that's what the quiz is about, to understand where that time dependence comes from. But in general, it will be time dependent. Okay, so in other words, what that means is that at this moment in time, let me wait a little bit more. At this moment in time, the particle is most likely to be in the center. But if I wait a little bit more, boom, right now, the particle is most likely to be either here or here. In other words, I prepare a bunch of particles, I have an ensemble of particles, and I decide to make a measurement now, okay? I will find most particles either here or here. Whereas if I prepare a bunch of particles and I decide to make a measurement now, I will find most of them at the center. Okay, so that's the superposition. So in general, you can superpose any number of modes. You can superpose, for example, like this. Okay. And if I run this, probability density sloshes around the well in some complicated way. Okay, so if I prepare a bunch of particles and then make the measurements right now, make the position measurement, well, this is what the outcome of an ensemble of position measurements would look like. The histogram would look like that. Whereas if I prepare a bunch of particles and make the measurement right now, the probability density would look like this. The probability density is time dependent in a superposition state. Okay, so that's the square well. What if I have a harmonic oscillator? We've discussed harmonic oscillator today. Again, well, first of all, if I make the harmonic oscillator steeper, which means omega naught is larger, which means basically I'm making the spring constant larger, or m smaller, right? So the natural frequency of the classic harmonic oscillator is increased, means I have a more steeper parabola. And we discussed that the spacing between energy levels is h bar omega naught. Okay, so if omega naught is larger, we're dealing with a stiffer spring constant, the levels are spread out. Here's the ground state, here's the first excited state, second excited state. It's probability density I'm looking at. And okay, so that's same story, right? You have some spillover into the non-classical regime, but it's not a great spillover. Particle is most likely to be found in the classically allowed region, except that there are nodes where it will never be found. But if I look at very excited, we discussed sort of a classical correspondence. If I look at a very excited state, the average of this matches the classical probability density. And again, I can mix and match. I can have a superposition state. So let's say 1, 3, and let me mix 7 and 8. There'll be some very complicated function of time. Okay, so the probability density, if I let go, will be some complicated function of time. So the way in which probability density changes will be complicated. Well, we can look at Coulombic potential. We can look at a Coulombic potential. Well, actually, before we look at the Coulombic potential, let's look at the asymmetric one. Let me reset. Let's look at, again, at just individual modes. So here's the probability density of the first mode. You see that it's asymmetric because the well is asymmetric. And you're more likely to find a particle on this slopey side than here, which kind of makes sense because there's the force, the stopping force is smaller on that slopey side. But other than that, the generic features that we discussed apply. Now, in general, the wave function is not going to be just like a pure sine or sum of pure sine and cosine waves. In general, it will be something more complicated. Okay, it's no longer sines and cosines in the classical region, but qualitatively, the wave function looks as we've discussed today, right? There's a spillover into the non-classical region, which gets larger the closer to the top you go. The number of nodes and antinodes increases, the curvature increases as you go up, decreases as you go down. You will notice that you can actually, if you think about it, you realize if I have a very deep well, if I look at a very excited state, it's almost like a regular well, but where the wave number and the wavelength continuously changing. Because you can think of this as just a bunch of sort of infinitesimal steps, each corresponding to a finite well of different depth. And for each depth, there's a wave number, and as the depth changes, the wave number changes. So you can see the wavelength and the wave number inside. You can think of this as kind of a sine wave or cosine wave where the wave number itself depends on the position x. So that's how you can think of these kinds of states. And we can also talk about Coulombic potential, right? So if this is, let's say there's a positive ion in the center and there's an electron. Well, that's what bound states look like. This is a simulation for bound states. So here's the ground state. Here's the first excited state, second excited state. Again, the same qualitative features apply. We can look at 3D Coulombic potential. It's more complicated. Okay, the structure is more complicated. So the 3D corresponds, classically, it would correspond to an electron orbiting a proton, like a hydrogen atom. But the 1D corresponds when the electron is confined to a line on one axis between the electron and the proton. But again, you know, qualitatively, the same features apply. So by learning by doing a lot of investment into what we did, you can start talking. You already have vocabulary to talk more mature subjects.